So welcome to lecture 2. Couple quick housekeeping things. So first off, my office hour time, the one I'm going to keep as a reoccurring one, will be at 2:30 to 3:30. I'm getting your room booked over in chemistry. That's the one for drop-in. That's the one that fits your time. If that doesn't match your appointment, or if that doesn't match your schedule, shoot me an email. We can set up a time to meet outside that point. That's my email address, as I mentioned last time. The TA run tutorials, we now have a room and a time. This is going to be Thursday from 4 to 5 p.m. in chemistry D213 every other week. First one starting January 15th. If you want to know other details and material for that point, please email the TAs. Their email addresses were in last class component. Again, any other components of how that's going to run, what content is there, please contact Sarah and Rebecca. They can work through those parts. Other reminder too, if you haven't done so far, please sign up for Piazza. Our last class. This is our introduction. Yes, sorry.
I just want to ask about the tutorial.
Yep.
I think that a lot of us have a lab at that time. Is it recorded? It's not recorded, but you can take. Okay, because I think that a lot of us have our lab on that.
So hands up if that is a conflict. Amanda, is it every week you have lab at that point? Okay, so flood their email address with please, please, beg, beg, beg. Okay, then we'll update that. Thanks for flagging that. So last time, we talked through a little bit about what got me into this, a couple bit of course information, and some very light introduction to organic chemistry. What we're going to do at the beginning of every class, roughly, is we're going to have one quick review question for you guys to work through. The way I want you guys to work on this is as follows. So here's the rules of engagement for these kinds of questions. This isn't based on clicker. It's not based on participation point. But these questions are really good things for you to try yourself first. Then I want you guys to work collaboratively about what the answer is. So usually what we're going to do is I'm going to put up a question. I'll ask you guys to work on it. Silent. Try to do this yourself on your own. I'll give you about a minute or two to work on it. Then I'm going to ask you to break, turn to the person next to you, and convince them why you're right and they're wrong. So I want you guys to work on it after. So don't worry about this. It's not for points. This is your way of doing a quick test of, do I remember this concept? Okay? And it helps to do this as you have to try and struggle first, then actually reach out, dude, what's a carbochemical? Do that after. So 1 minute. Try this on your own. What is the ranking? Most to least stable. I know I talk to myself, but on your own, do it yourself. Try to do this silently just to yourself. Don't work on this one part collaboratively yet. Okay, turn to the person next to you. What's the ranking? Why did you come up with that ranking? Explain your answer. Okay, time. So, I want to do this by vote the audience. This guy right here, most stable. Who thinks that's number 1? Okay. This guy number here, number in the middle one here. This is number 1. Okay, that looks like a popular vote. That means this one's out. Okay, number 2, second most stable. Is this second most stable? Show of hands. All right, that's good. 2, which makes this one 3, and that's chemistry 2, 1, 3. Ooh. There's levels. I don't do this anymore, but there was my very first exam I gave, multiple choice. I just went A, B, C, D, 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 and just that zigzag, and people started changing their answers. There's no way he did this. Okay. Now, why? Why? Give me a reason. First of all, did anybody does that surprise anybody? Again, you don't have to be embarrassed. Is this something you're like, what the heck is this? I kind of remember it. I do not. I put it backwards. Like, who said that is going to be your most stable? Yeah, okay, you outed him. That's okay. What's going on here? Why is this the most stable? You guys remember this from that? Yeah.
Like hyperconjugation.
Hyperconjugation. This is the word of that point. What we're saying is, okay, first of all, positively charged carbon, happy or not happy? Not happy. It's looking for help in any way it can get. How do you help out positive charges? What's a way to stabilize a positive charge?
Donate electrons.
Give it electrons. There are no lone pairs here, right? There's nobody nearby with lone pairs. So finding electrons means borrowing from other bonds. All you can do is find sigma bonds nearby and borrow some of those electrons on an averaging basis. So the more sigma bonds you have, the better. If I am this carbon here, I've got sigma bonds up here. These are not, I have no associated sigma bonds nearby that can sort of do sideways overlap. I've got CHs over here I can borrow from. Here I've got 2 CHs I can borrow from. Here I've got 3 centers of CHs I can borrow from. The more hyperconjugation, or the more sigma bonds adjacent to my positive charge, the better help I'm going to get. It's the best thing I can do in the absence of resonance or lone pairs or hyperconjugation is the lowest sort of part. So yeah, substitution pattern is what gives you this. A higher substitution, a tertiary carbocation. Does everybody remember that word? Tertiary, 3 things around it. This is a tertiary carbocation. This is a secondary carbocation. This is a primary carbocation. This is what we learn for things like SN1, SN2. Now we're going to come back to that part today. Now, quick thing for today, we're going to have a very brief recap of 123 and 203. This is just a quick reminder of different components and where the resources are. We're going to talk through the carbonyl group, nucleophilic reactions, cyanohydride formation, and carbonyl activation. That's what we're going to talk through on this one. As a reminder, these are things that you should remember. Molecular bonding theory, VSEPR, those are all things that we're going to be bringing up as you should know these things. Same things like factors influencing stability. That's what we just talked about right now. Electronegativity, polarizability. These are the same rules we gave you to rank how stable or unstable is a positive or negative charge. This is what also comes into things like pKa's. Remember all that. If you do not remember these concepts, I have linked my old Chem 123 video lectures. They're broken down based on titling. If you want to go and review them, they're on our Canvas site like that. Please go check those ones out. Those should still be available based on the old Canvas one. If you have any problems accessing them, let me know and I can repost them. So from 203, you guys remember the first principles of organic chemistry: substitution reactions, conversions, oxidations, reductions, labeling things as nucleophiles and electrophiles. We have principal reactions like eliminations now. These are where we're fragmenting bonds. Give me one thing that's different between a substitution reaction and an elimination reaction. What's different between these two things? Because remember, we teach them as kind of a pair, SN1, SN2, E1, E2. Yeah?
Substitution reactions require nucleophile, elimination reactions require base.
Yeah, that's a naming thing. That's kind of like saying, because we've gone through this part and you may have seen this. Bases and nucleophiles share a lot of the similar properties. What's a key difference between a base and a nucleophile? What makes something, when we call it a base, what is it doing that makes it uniquely a base? There's something that's very, very specific. Grabbing a proton, right? It's negatively charged. It's picking up a proton. That's what makes it a Bronsted base. That's that point. But fundamentally, a lot of the characteristics of strong base, good nucleophile, those are associated. That's why they're there. But yes, absolutely. Elimination reactions are usually, pulling something apart. Substitution reactions use nucleophiles. That's true. What about, kind of thinking about bond order. What types of bonds are involved? We're talking about substitution reactions. Sigma, pi.
Elimination reactions
Exactly. Substitutions like billiard balls, sigma bonds are being broken as new sigma bonds form. It's all singles, right? We're taking a carbon that's tetrahedral and we're just subbing one for another. But we're really dealing with the sigma skeleton. Elimination reactions, on one way, we're starting from sigma and we're forming pi bonds, right? We're making double bonds as we do that. We're going from an sp3 center back down to like an sp2. Remember those hybridization points? So the bonding order and what's associated are different. Exactly. Now, if you have any issues and stuff like that with these other components, like I said, one of the resources you have is my old videos from 123. I've linked on the Canvas page as well, things like the pKa values you're expected to know. These are relative to certain functional groups, and these are good baseline ones you should know at the drop of a hat. These are things, again, you should be able to go to the bar and like, hey, you know what the pKa of a carboxylic acid is? It's a great pickup line. But again, you want to know these ones. Again, they're the rules we gave you about how to rank them based on stability, but knowing these are really good goalposts, things to have in your head to help you to rank what is more reactive or less reactive, what is more stable or less stable. Those are really important things to have at your fingertips, so you should know these. Whoops. Also, if you've come from Chem 233, there are a couple of reactions that were covered in one but not the other. I've linked in a document of if you're coming from 233, these may be concepts that you do not know quite yet, or these are things that you might want to review on. So there's an information handout on that part as well too. As far as where we're going to be, this is where in the Volhard textbook we're going to focus on for the next little part. So it's going to, talking aldehyde and ketones, that's over here in chapter 17. The old Brown textbook was chapter 16. We're going to work our way through carboxylic acids, that's 19, 20, 23. Brown, that was these ones. And then aromaticity, 15, 16. This is kind of the whole scope of what we're going to be doing over the next couple of weeks leading up to the midterm. So this is just meant to be a goalpost to show you what kind of chapters we're going to be dealing with, focusing first of all on this chapter 17 kind of part of the Volhard book. All right. This is a carbonyl group. Does that surprise anybody? So quickly, what is the difference between a functional group and calling this an aldehyde? It's a naming thing, but what is a functional group? Again, your mom calls you up and says, I'm paying all this money for UBC. What's a functional group? What is it? If you had to define it, or again, tell it to the person, your neighbor, what do you got? Okay. So now that you've had a chance to poll a friend, I want an answer. What's a functional group?
A site on the molecule where you can form reactions.
Yeah, that's a good part, right? Do aldehydes contain functional groups? Like an aldehyde has a carbonyl, right? That's the nomenclature we're saying. A ketone has a carbonyl. It's a piece of the molecule. Functional groups are made up of more than one atom, usually, and certain kinds of bonds. A carbonyl, in particular, is made up of a carbon and an oxygen, so those are the constituent components you need. A carbonyl has to have a carbon attached to an oxygen with what kind of bonds? Sigma, pi, one of each, right? It has a bonding order of 2. It has one carbon-oxygen single bond, one carbon-oxygen double bond. That's what makes it a carbonyl. There's many functional groups that contain carbonyls, but on their own. This carbonyl group is the slowest little piece we need. To call it a ketone specifically means you got a carbonyl flanked by 2 carbons. Carbons, most importantly, not nitrogen one side, hydrogen. To be a ketone means these have to carbons on both sides. Aldehyde, carbon, hydrogen. So the overall naming of something like aldehyde, ketone, means it's made up of these pieces of other parts. The naming we give it to it tells you about things like reactivity. Certain reactions will only work with certain functional groups because of the atoms and bonds that are involved in them. That's why we have these things broken out. All right, so tell me about this. This molecule is called acetone. Somebody give me something you know about acetone. What's its IUPAC name? Yeah.
It's a common solvent.
Okay, common solvent. What does it smell like? Say acetone. Yeah. 2-propanone, right? It's a ketone, right? That's why we call it a ketone, because carbon's on both sides. What else?
It's used for nail polish removal.
Nail polish remover is probably where you've run into it. Absolutely. What's the other fun fact? Nail polish remover, yeah, acetone's a big one. What's the other main nail polish remover? Smells a bit fruitier, not acetone. Like anybody who's done, I do my wife's nails all the time. Acetone smells a very certain way. Then some other people may have looks like a foam. You dip your nails into it. Smells a lot fruitier. Do you know what that solvent is, by the way? It's ethyl acetate. Woo, take that one later. It's an ester. Come back to that one later. But yes, it's a common solvent. It's flammable. It's a ketone. These are all properties of something that comes down to, these are properties engendered to it because of what this molecule is. Now, if you talk about bonding order and stuff, this carbon here and that oxygen, they have a dipole, right? Do you remember dipole moments and other things? Which way does the dipole go? Which is more positive and which is more negative? Yeah, oxygen is going to be more negative. The carbon then is going to be more positive. Why? Because there's a dipole moment across that bond. Oxygen is more electronegative. Carbon loses that battle. It polarizes the bond across it. That positive and negative is important because those are the sites that reactivity happens. Reactions, any reaction is just sharing and moving around electrons, which means you have to be able to look at a molecule and find sources where negative charges and electrons are and sinks where they want to go. So this means nucleophiles are going to attack the oxygen, right? Yeah, there you go. Yeah, that was the catch-up. Wait, no. Nucleophiles will attack because... So that's the thing. Being able to look at a molecule and find positive and negative is critical. Electrophiles will go after the oxygen because it's negatively charged. Nucleophiles go after the carbon. These are the sites and reactions that you're going to have. The other thing, too, do you remember about HOMO-LUMO energy theory? HOMO-LUMO, highest occupied molecular orbital, lowest unoccupied molecular orbital. We define these because that's where those electrons are at the outer fringes. They're the outside. That's where reactions happen, is with these outside ones, not the core, not the ones that are sort of at the main part of this molecule. The ones at these highest occupied molecular orbitals are the ones that will be displaced by reactions. They're the ones that are exposed. Turns out these double bonds, that's mostly the most exposed places. That's where reactions will happen. So these carbonyls means that anytime you see this, this is where we're probably setting up or running the reaction. It's the most easy to do chemistry on. If you remember how it looks, the pi bond in particular is a really unique feature of it. It's not an alcohol. Remember, alcohols are single bonds across here. This carbonyl has this pi bond. It has a double bond across it. That pi bond is going to occupy both the highest occupied one, a bonding relationship in this kind of looks like a hamburger, right? This is an sp2 carbon where you've got this pi bond populated across that whole space. The antibonding orbital, the lowest unoccupied, will have a node between the two. There are electrons sitting here. Remember, you actually do the Lewis dot structure of this. This is populated. This is unpopulated. That's why we call it the lowest unoccupied molecular orbital. There's no electrons there, but it exists. It's still present. It's this kind of dark, lingering thing that on some days you can actually use this, but there's no electrons there now, so it doesn't have any of that character yet. So if we're going to use this, and again, we're talking about these being our sort of centers where chemistry is happening, there's really only two ways to break a bond. Any bond either is going to break because you remove electrons from an orbital that has electrons, so we're going to be pulling it out of here, or we push electrons into an unoccupied molecular orbital, specifically an antibonding orbital. So if I'm going to play around with the pi bond, it means I'm removing electrons from this guy. I'm getting them out of the pi bond. So that's where your arrow is going to depart this. And you're going to be adding electrons, so arrow coming in, to an unoccupied molecular orbital. What you're doing is you're reshuffling the pi system. So this is the number one thing carbonyls do. Much like the backwards reaction of your elimination reaction, you're taking a pi bond and you're going to be splitting it up by adding electron density here and breaking this pi bond. That's what most of the time we're going to do. So what's the reactivity trend here? These are now sp2 centers. We got formaldehyde, acetaldehyde, and acetone. which one is the lowest reactivity, would you expect? Towards nucleophiles, yeah. Acetone, lowest. Okay, state your case. Why? Okay, good point. So remember, each of these is a carbonyl. Each of these is going to have, each of these is going to have a delta minus up here and a delta plus down here. That's the nature of the carbonyl. The magnitude of each of these is basically talking about how stable or unstable things like the negative charge or the positive charge is. Now, if we go across this list, there's really nothing that's going to change too much about this. The oxygen center over here, there's not a lot of other stuff around it. The real difference is nearby this delta plus center. And remember back at the beginning of class, we talked about stability of carbocations. These are not carbocations, but they're similar enough to have similar reactivity trends. So if I have an acetone center here that's delta plus, and I've got hyperconjugation, a bunch of sigma bonds nearby, those sigma bonds will stabilize this center in the same way that hyperconjugation stabilizes carbocations. They have the same reactivity and rules and trends. So this goes back to one of the things I said last class. You don't have to memorize every single concept as unique. Find a core concept, the stability of carbocations, hyperconjugation, and find out where it's used over and over again. So the same rules apply. Formaldehyde loses because it's a primary carbocation. This is next because it's a secondary carbocation, like that. This is like a tertiary carbocation. So hyperconjugation is definitely a big one. There's one more nuance that's a little bit different about this. Comes back, you might have seen it in SN2. Steric hindrance. If you guys remember, a tertiary center, like let's say, if I took this tertiary bromide, and I tried to do an SN2 reaction on that tertiary bromide, I got a problem, right? The nucleophile cannot approach this center to do that bond-breaking bond formation. Sterics is a problem. There's a little bit of that going on here too. Hyperconjugation means this is more stable. Sterics means it's also partially shielded. If you're going to do reactions at this center, I'm going to have the nucleophile approaching this. So you're kind of mixing and matching both the things from SN1, SN2, E1, E2. Same pieces. What about these guys? These are other functional groups. Acids, amides, esters. Again, we'll come back to them in more detail later, but notice they all have carbonyls. The difference is they are not ketones because we have carbon nitrogen for amide, carbon oxygen for an ester, where that is another carbon, or carbon oxygen hydrogen for carboxylic acids. Why are these, in general, we rank these ones as much less reactive than aldehydes and ketones. They all have carbonyls. They do a lot of the same chemistry. They are way more stable. They are less reactive. Why? What makes these things more stable? Look next to it. Remember what we said back here, the positive charge nature. More positive, more reactive. Hyperconjugation helps it out. That makes it less reactive. If you go down here, okay, these all probably have hyperconjugation, RRR, right? Look at this. I have a lone pair. These are unique because every one of these has a lone pair adjacent to that center, which means you've got resonance. I can draw a resonance structure where that R group, or that lone pair, is physically donating into that pi structure. The lone pair adjacent in all these cases is actually part of the pi bonding network. It's helping to reinforce this bond here because it's adding double bond character. It means that that poor delta plus is being partly helped out by actually borrowing that lone pair for some period of time. So these guys here, yeah, they have hyperconjugation, but they also now have resonance. So having these lone pairs next to them gives them a full different name. That's why we put them in a different category and a different even functional group name. Because yeah, they have carbonyls, but they're different because of this other intrinsic property. They can now use hyperconjugation and resonance to help them out. Yep, good stuff. So how these nucleophilic attacks happen. It looks a lot like SN2. You're going to have two arrows. There's going to be a nucleophile approach and a bond breaking. You need to have both. So again, quick question. What if I didn't have this one? If I only drew this, what's wrong with that notation? What's wrong with my syntax there? Nucleophile approaches, and that's all I draw.
You would exceed not the octet rule.
I'm making a Texas carbon. I'm making a carbon that's bigger and better than normal carbons that has 5 bonds and doesn't exist on planet Earth. Yes, we're breaking octet. We can't just stuff in more electrons. We have to also break the pi bond, right? So they're coupled together in the same way that for for SN2 reactions, you've got the nucleophile approach and some leaving group. Here, you don't have a leaving group. You're using the pi bond as that property, right? You're breaking this one. So any nucleophile approaching it will look like this. The first step, first move for a nucleophile approach will look like this. And that is common for aldehydes, ketones, esters, amides. You'll see it over and over again. Every time a nucleophile approaches a dipole, it's going to attack the positive charge end over here, and you're going to have this in-out behavior. So what makes things different is how good or strong these two partners are. This is where we have to match a good electrophile and a good nucleophile to see which way the equilibrium sits, or if we have to do other things to the system first. So in general, if the nucleophile is also a good leaving group, if it's a relatively stable negatively charged, then this will be an equilibrium. It can add and fall off, add and fall off. So give me an example. What is a stable negative charge? What's a common ion, anion that we might give you that you're like, yeah, that's not a really bad anion. It's relatively stable. It's probably a reasonably good leaving group.
Bromine.
Not bromine, bromide, Br minus. Yep, that's one. What else? Chloride. Give me another one. Iodide. Okay, non-halogen. Yeah. Hydroxide. Is hydroxide a good leaving group? Remember, back to SN1, SN2? No, we don't usually put. You can make it into a better leaving group. We have to protonate it, right? But not hydroxide. Give me something else that's not a halide. Yeah. Hydronium ion. Yeah, that would be a good leaving group, right? Like that's the departing. But yeah, absolutely. What else? Tolzolate. There we go. Hydroxide's not a good leaving group, but you can make them into good leaving groups by giving something to stabilize them, right? Carbonyls, resonance stabilization at O- is how we do it. So converting a hydroxide to a tozolate would be what we would go to. Absolutely. But what I want to emphasize is, again, anything that's negatively charged can add, but it can also eliminate. Where it sits on this equilibrium really comes down to, is this side more stable or is that my side more stable? This is where your pKa's are really useful, because O- like this, that's the conjugate base of what? If I gave that a proton, what's that functional group called now? Alcohol. So knowing things like the pKa of alcohols is really important for ranking relative stability. O-, that's just my conjugate base of that's like hydroxide. It's like hydroxide with other fruit hanging on it. So if you've got something like chloride, chloride's probably not going to beat hydroxide. If you added chloride, sure, that can happen, but then it's going to easily kick it out and kick that chloride back out. Equilibrium is going to sit on this side of the equation for chloride because you're ranking the relative stability of those two negatively charged species. If you do have a good leaving, or the nucleophile is not a good leaving group, this is one way, or at least it's very, very, very product favored. So an example of this one would be something like what? What's a good nucleophile? If you had to go to your bag of tricks and you're creating a reaction, what are you going to grab as a really good nucleophile? Which one? Cyanide, yeah, carbon minus, that's not bad. What else? Thiol, yep. So sulfur is a good nucleophile generally. Sulfide, yep. And nitrogen? An amine, yeah. I want you guys to go crazy. These are not bad. I want you to go to something that might start on fire that is so ticked off. Like, what's something that's really, really bad? Yeah. Grignard reagents. There you go. Go to the nuke option, right? So alkyl lithiums, carbon minus. These are not friendly things that are really good nucleophiles, because C minus is nothing usually. If there's no resonance, anything helping it out, carbon minus are really great nucleophiles. Yeah. good nucleophile means negatively charged, right? Not a good leaving group means it's not stabilized by anything. It is a negative charge that has usually, good nucleophiles are usually conjugate bases of very, very, very weak acids. So things like CH, methane, for example. If you deprotonate methane, you get CH3-. That is a pissed off molecule, right? It's looking for that proton back very quickly. So anything that's very strong bases usually fall in that same category as really good nucleophiles as well. So what we're saying is in this equilibrium, an example would be this. A Grignard reagent is a carbon minus species. That's taking if I took phenyl magnesium bromide is kind of like phenyl minus magnesium bromide, right? You can separate out to an ionic species. So really a Grignard can be thought of as a source of carbon minus. If that adds to the species, if I add this in, the arrows I'm going to get is nucleophile attacks here. This bond is going to displace. That's the intermediate I generate before the workup of this reaction. If you notice here, all we're doing is we're just doing an ionic balance. That center there, O magnesium bromide, is really just O minus magnesium bromide. And again, in this process, we're really saying what's more stable, carbon minus or oxygen minus? Carbon minus is way less stable. Oxygen minus is more stable relative in this pair. That's what makes this equilibrium go forward. When we say workup, all we're saying is give it protons. The molecule will stay here. It will wait until you give it protons to break up this ionic complex, give it back its proton. That's going to be your product here. You make your alcohol from this. So this is a standard carbon addition that you get from this. Same thing, like alkyl lithiums and alkyl halides and alkyl Grignards all do the same point. This is also we pointed back. Remember, these are really, really basic species. They act to just deprotonate things as well, and that's where there's a commonality between good nucleophiles and strong bases. They're strong or unstable negatively charged species. So it also means if you had things like other acidic centers, if I did this reaction where there were simple protons to deprotonate, that Grignard is going to have a choice. Does it want to react with the carbonyl in this way, or is it just going to find a proton somewhere and grab that? This is where you're going to have to design the nuance that comes in with these reactions. Yes, Grignard reactions can add to ketones, no problem. Remember, the nuance comes in if there's acidic functions, what is over here is what changes the specificity of certain reactions. If there was simple carboxylic acids over here, now this reaction becomes more complicated because it's going to be competing with those protons, right? In general, reductions using something like sodium borohydride. Do you guys remember simple reducing agents like sodium borohydride, lithium aluminum hydride, maybe? This is where the hydride, H minus, is your nucleophile. And what you're doing is you're taking hydride, adding to this carbonyl to make this species. It's the same basic property as your Grignard, where effectively one of these is my H minus nucleophile, and I'm adding that proton to the center to give me the oxygen-bound species after. And then from there, workup is just adding a proton to cleave this bond to give me my product over here. Both aldehydes and ketones compete in this point as well, too. Alkynes. This is another form of carbon minus. Remember, sp carbon centers like this, that negatively charged is a little bit more stabilized than normal carbon minus species. But again, it acts like a surgical C minus attached to the center, forms an intermediate that then gets protonated. Once again, the arrows are going to be nucleophile in, arrows come up. That can be thought of as O minus, sodium plus, and then on workup, you're seeing a proton. So the thing I'm trying to emphasize here is there's a common pattern. Simple nucleophiles will add to these carbonyls. You're displacing or breaking that pi bond that leaves you with an intermediate that had better be more stable than the thing you started off. That's why this energetics moves in this way. You're making O minus and you're trading it for carbon minus. And then your workup is just getting rid of those last charges by adding protons, weak acids, to give you back your product over here, right? So the main one we're going to focus on now is your kind of first focus reaction. This is cyanide addition. This is forming cyanohydrins. If I take a carbonyl, and as we mentioned at the very beginning, I can use something like cyanide. Now, sodium cyanide is a fun and delicious snack. I'm kidding, please do not do that. It's an ionic compound made up of sodium plus cyanide minus, which means the cyanide part of that ion is your nucleophile. So there's my negative charge. I'm going to add it over here. Fun fact, if I just took, look at the conditions here. What am I actually, let me drill back to that. I'm showing you some structures. This is my ketone. Over here, I'm giving you a new molecule. It's called a cyanohydrin. It's basically an alcohol with a cyanide attached geminally to the same center. Gets a special name because we do special things with it. Look at these conditions. Is this an equilibrium or a one-directional product forward-facing reaction? What am I saying? It's an equilibrium. What does this mean? Not a trick question. The pH is 8. Basic, acidic. Very basic or very acidic, or mildly basic? It's near neutral, right? What's this mean? Sodium cyanide is the thing I've been focusing on. What's that? It's the conjugate acid. So on here, I'm giving you reagent conditions that include both the nucleophile and its conjugate acid. That's important. I'm telling you the reaction has to run not acidic, slightly basic, right? This is really important because if I just took that ketone and I did not have this at all, it was just the ketone and just sodium cyanide, nothing's going to happen. Okay, I'll give you that as a fact one. Think about that as why. There's another one that's a lot easier to focus on though first. The other side of this, if I go back, if I was to not include this, let's say I'm going to do it under very acidic conditions. Why is that a bad day? If I took sodium cyanide at pH 0, very acidic, we just said that these two components are my conjugate base and conjugate acid of an acid-base pair. If I have the pH very low, very acidic, well, that means that cyanide's probably going to pick up a proton, right? That's easy to do. The pKa of sodium cyanide is about 9.5. So the lower I go, down closer to 0, means this equilibrium between sodium cyanide and HCN lies in favor of what? What is more stable at very low pH? HCN or sodium cyanide? HCN, the acidic form of it. What is HCN? Solid, liquid, or gas, first of all. Does anybody know that point? So nobody's, again, I'm glad. This actually means you guys are, either you're lying to me or you're nice and innocent people. Sodium cyanide is cyanide gas. It is a gas. If you take sodium cyanide and drip acid on it, it creates cyanide gas and you die. So if you do this reaction in the lab and you get that part wrong, that's your last day in the lab. That's just the practical outcome of this point. So that's rule number one, is why don't we do these under acidic conditions or two acidic conditions? Because it will kill you very quickly. But I'm still, look at the pKa. pKa of HCN is 9.2, right? That means this is actually sitting as sodium cyanide plus a little bit of protons, right? They're still there, is going to make HCN and water, right? If my pH is at pH 8, am I above or below the pKa? Again, this is not a trick question. pKa is 9.2 for this equilibrium. pH is 8. I am below the pKa. It means I'm not fully on the phase of the base, but I'm probably the basic side of it is going to be favored. It's about a 10-to-1 ratio. If you actually go through the Henderson-Hasselbalch equation, you calculate the concentration of HCN to CN minus, given this pKa and that pH, you'll find that the ratio of A minus to HA is about 10 parts A minus and only about 1 part HA. That is critical to get this reaction to work. So I've given you two facts here that are really important. One, don't make this too acidic because you will kill everybody else in the lab. That's one, that's easy. But if I don't have anything, if I ran this up at pH of 14, I'm like, oh, I'm so scared of HCN, I definitely want to make this pH really, really high. The reaction also doesn't work. What's going on? So let's go back to, oh yeah. The carbonyl is not reactant enough. That's right. Remember what we said back here. If the nucleophile is also a sort of good leaving group, this is a reversible reaction. It can add and fall off, add and fall off, add and fall off. And depending on the relative stability of that negative charge and this negative charge, the equilibrium will either be more product favored or more reactants favored, right? So now we've given another fact. What was the pH or pKa of hydroxide? Well, remember alcohols. What's the pKa of an alcohol? Yeah. 15, 16. Yeah, absolutely. So go over here. We just said, I am making, as an intermediate, before it protonates, before it works up, I'm making O minus. The pKa of an alcohol is about 15, 16. HCN has a pKa of 9. CN minus is more stable than O minus. So if I don't have anything else helping this reaction out, if I just took CN minus, the real thing I'm doing is I'm saying, I'll go over here. What I'm really saying is, if I take a carbonyl and I don't have this present, sorry, let me do it this way. Bloop. I don't have any CN present. I'm forgetting about this. I'm saying it's, let's say the pH. Let's say the pH is equal to 14. I'm saying CN minus has to attack here to make this. That will be an equilibrium where I'm going to have O minus, CN minus, and my proton. So what I'm saying is, what's more stable, CN minus or O minus? What we've decided from the pKa's is hydroxide, O minus, is less stable than C minus, cyanide minus. It has, it's an sp center, it has a nitrogen next door, there's hybridization. It's not a bad anion, it's a relatively good leaving group. It's right in that middle pocket. So we can't just force this the same way we can with Grignards. We can't just take a negatively charged carbon and ram it into this carbonyl. That's why we have these conditions where I run this reaction in this kind of weird middle buffer space. That pH 8 is critical for this because we have two moves here. If you remember back to SN1 reactions, if I have an alcohol and I really want that to be a leaving group, what do I need to do to the alcohol? I need to protonate it. This is the same thing back to like SN1. If I don't have a good leaving group, if I've got this problem where the thing I'm forming from that addition is not as stable as I want it to be, you need to do a move ahead of that. These conditions mean that I have ready to go protons. I'm usually running this in the place of H3O+. This kind of buffered conditions means I've got a little bit of this kicking around, which means the first move I'm going to do is I'm going to take my HCN and I'm going to use it like an acid. So now I can protonate my center. I'm adding a proton to my carbonyl, and I'm getting it ready for the attack. So instead of just a direct attack the way that you would have with a carbonyl and a Grignard, back to like you saw with SN1, I activate my carbonyl first, I protonate it, now I have a better electrophile. I'm using the protons available to supercharge my center. Now I've got my CN minus, now I can do my attack. I've amped up the electrophilicity first, I've made that carbon plus better, it can attack into it, I get my normal bond formation, now I get my product. Just as a quick suggestion too. This goes back to why you should be drawing your mechanisms and practicing on it. As you're working through, like what I used to have to do in grad school, we used to have what was called comprehensive exams. Your prof would give you a problem, say go to the board and figure it out live. It's the first time you've seen it. The trick you have to learn in that moment, start slowly drawing the part of the molecule you're sure of, and then add in the part you're trying to figure out. What I mean is, when you're doing these mechanisms, a really important thing, a practice to get into. If I am saying, here is my starting material, and I know the reaction is happening here, start by redrawing your sigma skeleton, the part of the molecule that is not undergoing change, then focus on the part that is changing. So here I'm doing my addition. That's why this is the last part that I draw in. This is a really important hygiene question for you guys to do, because during midterms, when you guys are rushing, you know how many times I've seen this molecule suddenly gain sulfurs? Recopying errors suck, because what it means is I don't know if you just made something up or you just happen to recopy it. It's very difficult to start avoiding part marks if you suddenly do a total transformation over here just because of how you recopied it. It's a dumb mistake you can make really easily that you should just slow down, practice redrawing your structure, and practice drawing your mechanisms when you do this. This is one of those, just again, tips to do as you sort of work through this part. But that's the distraction. You still get the addition. It looks like the addition you'd get after that normal part, but you're starting off, you're leading it with this protonation in this case, and that's why we have these conditions that are specialized into this case. So, under these two, and this is the last one I'm going oh, no, we got a little bit extra time. We can talk through this. Both of these ones undergo reversible additions. That first addition is going to be reversible. Which one of these do you think is going to be more reactive? If I have to react to make the cyanohydrin between these two, which one of these do you think is going to be easier to do that addition? Which one is harder? You think this one is easier to react with the cyanide conditions that we have. So we've got one vote for this. Show of hands. Who agrees? Okay. Anybody want to be on team aromatic? Why not? You're right. Why? What's that? Well, okay, elimination, yeah, it's not going to react over here. In both cases, we're focusing on the carbonyl. So the real thing we're saying is, why is the nucleophilic addition, why does cyanide addition here, why is that not good compared to, I'm not saying it doesn't happen, it's just definitely going to be less efficient. The equilibrium of that first addition is going to be more starting material favored than this addition. This is going to be definitely better. Remember, we still have to protonate these in both cases. We're going to have to protonate them as our first step in both ones, but this one here is definitely going to be better. Give me a reason. Yeah, this goes the other way, right? Remember, we said cyanide on its own can't attack a carbonyl. It's not nucleophilic enough, doesn't help out. So what did we do? We added a proton to the carbonyl. We increased its electrophilicity. Okay, cool. Now we've done that to both of these. We've increased their electrophilicity. This one here has all this help over here. The aromatic group next to it is doing something else. It's stabilizing the carbon plus that you get over here. So remember, this is just an energy level diagram you have to keep in your head. If I am sitting at some energy state and I'm going to my product, which is downhill, okay, that's a product-favored equilibrium. If my starting material is way downhill because it is stabilized, it's harder to get out of that hill. So having a very stabilized starting material where the carbon plus center I'm looking at here is now being stabilized by this resonance, I've just put up a shield that makes that nucleophilic addition harder. This is kind of like what we talked about. Boop, 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 boop. Here. Right? Having electrons next door adds in electron density to my carbonyl, which prevents reactivity. Having that benzene there is not a good thing from the perspective of reactivity in this sort of case. Again, why I'm emphasizing this is we get stuck in these ruts of like, oh, stable, not stable. Yeah, benzene is stable. Resonance is a good thing. Not always. Not if it's hurting where you need to go. All right, that's it for today. I will see you guys on Friday. Hey guys, so I wanted to quickly touch base on one note from class and just clarify one item. So first, I think I misspoke. I just wanted to double check. If you notice, the reactions are run at pH 8. The pKa of HCN of cyanide gas is 9.2. That means that the reaction is actually on the acidic side, where it's below the pKa. So remember, for the pKa equation, we're talking about the speciation of some acid, in this case HCN, excuse me. One sec. Redraw that. So it's HCN And if it's acting like an acid, remember the pK equation means that we're donating a proton to water. And the Ka expression would be redrawn where we have the hydronium ion, H3O plus, and cyanide, the conjugate base, Cn minus. So that's the equation where we derive this 9.2, which means if we were to look at this using a normal sort of Henderson-Hasselbalch equation, your HA, that's your HA species, your acid. This is your A minus species, and if we were to use the Henderson-Hasselbalch equation, we could calculate the ratio of HA and our A minus, the acidic and the basic form of this weak acid. Remember, if you're below the pKa, we should have more of the acidic form. So as this reaction is running, we're going to have approximately 10 times the acid form and only 1 of the base. So it's actually favoring the acidic form of this equilibrium. So again, just saying here, that means we're going to have about 1 part of the nucleophilic cyanide and about 10 parts of the acidic HCN dissolved in solution. The other part I didn't directly mention, we'll talk about a little bit more in class on Friday. Usually the solvent for this will be something like water or some type of an alcohol. It's usually what we're using for this kind of a reaction. So that's partly reflected by this pH. Remember, a pH is talking about the hydronium ion concentration, which generally means there's water around in order for us to calculate that concentration. So again, first thing there was just, I think I mentioned in class that the base form was favored. Remember, no. In fact, the pH, because it's lower than the pKa, the acidic form will be our favored one, but we have both of these two present. So I just want to touch again on this last point because this is a really key feature. First off, all reactions with carbonyls, in terms of our addition, they follow the same kinds of patterns. So if this was either a proton, like an aldehyde or a ketone, all the nucleophiles that we're adding to these ones will always have this kind of nucleophile attack and then bond breaking, very much like an SN2 kind of reaction we've seen in first year. The product of this addition generically, like we've shown, will equal our Nu minus, R, and whatever the last species here, call it H or R, depending if it's aldehyde or a ketone. So the thing you have to consider here, first of all, if this is going to be reversible, really what we're doing is we're weighing the stability of the anion we're forming and the nucleophile we start off. So the relative stability of this negative charge compared to this negative charge is going to give us some balance of which side this equilibrium is more or less favored. You could relate this back to an energy level diagram where, let's say we're saying we're dealing with, let's say, phenylmagnesium bromide, like we discussed, like our Grignard reagent, magnesium bromide. Now remember, that is sort of equivalent to phenyl minus. Negative charged carbon like this is a very, very unstable system. So I might be able to draw an energy level diagram where this nucleophile, this negative carbon, is going to be very high in energy, and then we're making an oxygen minus, which is actually going to be kind of low in energy. So as a result of this, what we've done, is we started at a high energy state, and by running this reaction, we're actually generating a more stable product. So in fact, this equilibrium is going to be very, very product favored, to the point where it's not reversible anymore. We can consider this as a one-way, irreversible reaction, and that's really just because of this large difference in energy between a very unstable starting material and a very stable product. So that's the first principle we're trying to teach out today. The second one is, let's say we're going to now use the addition of an aldehyde, and we're going to use, like we described, cyanide. Now Cn minus, and if I drew that in equilibrium with O minus Cn and H. If we look at the relative stability of these two, as we sort of mentioned, the pKa of our Cn is going to be 9.8. 9.2, something like that. And our oxygen minus, the pKa of its conjugate acid, an alcohol, is actually going to be 15. Remember, these two pKa's are referring to, in this case, it's the pKa of an alcohol, the acidic form. This is actually the conjugate base shown here. The pKa I'm referring to here is HCN, the conjugate acid of the cyanide. Either way, what we're saying is these two pKa's refer saying that this is actually going to be a stronger acid than my hydroxide. And by that logic, the conjugate base should be more stable. So in fact, this is not going to be a full one-way equilibrium. We're kind of almost walking uphill, right? We have the cyanide, which could be at sort of this kind of energy level, if we were to draw that same sort of diagram. And the product is going to be not massively different, but still less stable. So we actually have something that looks more like this. Now this is going to be more like a true equilibrium, or at least that there's a negative, there's negative pressure to do this, right? The starting material actually is going to be more stable in this equilibrium than the product. So this is the first case where the nucleophile in this case is not that strong. It's actually a reasonably good leaving group, which allows this to be a reversible reaction. That's why we need a little bit of extra help. We're not going to run the reaction strictly by taking an aldehyde and then sodium cyanide. This is where we need to actually activate the carbonyl in advance. So if we have one of those cases where I'm trying to use, let's say, a weaker nucleophile like the cyanide, what I have to do, I'm not able to go directly. I can't run that reaction just because of what we discussed. What we're going to have to do is actually make this acidic, or we have to make this activated by first basically giving it a proton. I'm going to show it simply as just H plus for right now. So picking up a proton there creates now our protonated carbonyl like this. And now we still have our Cn minus in this situation. So back to the energy level diagram, what we've done in this case is we started off with cyanide, or negatively charged species, at let's say an energy level like this. We've then made it less stable, or made this side of the equilibrium less stable by actually increasing the energy to an activated species. We've cranked up by making this thing less stable by making it protonated first. So we've activated the system. And now we can do the addition to that system to create the cyanohydrin product. We have our alcohol center, our Cn, and our proton. This is now going to be, first of all, it's neutral as a product, so it's actually going to be nicely downhill here. So this new energy level diagram allows us to go, first of all, activate the carbonyl, and then go downhill energy to a stabilized product. So we have created a different mechanism here. It's different than the direct addition that we're trying to talk about here, where a negatively charged nucleophile creates this negatively charged intermediate, which would then work up. Here what we're doing is we are protonating this one in advance and then doing the addition. And this needs to happen whenever we have a nucleophile, which is also in this category of a reasonable leaving group. So that's why if we took something like our aldehyde and we're trying to add something like sodium cyanide to it, we're going to do this in conditions at pH is equal to about 8. And because it's under those conditions, as we discussed before, that means we're going to have enough protons present to have a weak acid, HCN, present here, which is our proton or acid catalyst in this case. Really, what we're saying is I have to activate this carbonyl. We went through that discussion. It's not active enough to undergo nucleophilic attack. If we're going to activate this carbonyl because of the delta negative charge over here, an easy way to do that is by adding a proton. If we just added the proton here, the challenge we run into is that protons here will interact with any form of base, any form of extra electrons. And so yes, the lone pairs around this oxygen allow us to possibly protonate it. It's just it's not going to be completely selective. If we add protons to the system by adding, let's say, HCl or something else, remember the cyanide on its own, Cn minus, can also itself act like a base. It can pick up that proton, which is going to generate HCN. So when we show this condition, really what we're saying is an acknowledgement that we know pH 8 here, we're really saying that I have to have some protons around. If the pH was too high, I would only have this cyanide form. Since I'm going to have some protons around in order to do this activation, it means that the cyanide may act as a base also. It was going to exist where the proton is going to be sitting on the cyanide center. So this is just an example where we're trying to bring together a bunch of different concepts that are all happening in the flask at the same time. You have the need to activate this carbonyl because the energy level of the nucleophile would not allow it to simply add. We have to activate that center first. Because we're adding protons to this activation, there is the possibility of acid-base reactions happening at the same time, which allows both protonation of this carbonyl, but also protonation of my nucleophile to give me this HCN. So this is why we draw or represent the reaction conditions with both the HCN, the conjugate acid, and the cyanide at the same time.